Welcome to our final Chapter 7 video. Let's take a closer look at the sampling distributions of the sample mean, and then we'll look at the sampling distribution of the sample proportion. Let's get a couple little formulas out of the way here. So first thing we're going to talk about is the sampling distribution of the sample mean, which is quite long, so I'll usually write that SDSM. Alright, first thing we're going to look at is the assumptions in order for this to be considered normal, approximately normal, and allow us to use the Z tools with it. And those assumptions will be that either the population is known to be normally distributed, or our sample size is 30 or more. So if the population is known normal, sample size less than 30 or greater than 30, we'll consider that distribution of the sample mean to be normal, or any sample that is 30 or greater sample size will give us approximate normality for the sampling distribution of that sample mean. Alright, let's take a look at the mean of the sampling distribution of the sample mean, mu sub x bar. This one's a pretty easy one. This one corresponds to the population mean, equals the population mean. Alright, let's look at the standard error of the sampling distribution of the sample mean. This is a new concept now, standard error, so we've been used to dealing with the standard deviation, so that is going to be the numerator of our standard error, and what we're going to do is take the sample size, square root the sample size, and divide the population standard deviation by that square rooted sample size. That will then give us our standard error. And let's go over a couple formulas here. So very similar to Chapter 6, we're going to compute a Z value based on one specific sample mean value and its difference between the mean of the sampling distribution, and we'll divide that by one standard error, and that will give us our Z value. And what we can do here is rearrange this. X bar is equal to Z multiplied by the amount of the standard error added to the mean. Alright, let's take a look at our first exercise, and let's see what's going on here. So Business Week reports that its subscribers that plan to purchase a new vehicle plan to spend a mean of $27,100. Assume that the new vehicle price for the population of Business Week subscribers has a mean of $27,100. Notice this is mu, so that tells us population, or verifies population, and has a population standard deviation of $5,200. So I've circled these to note them, and let's head down here to part A. So this one starts out, what is the probability that? So when you see that, think that you know that the answer to this question is going to be some probability. So it will have to be greater than 0, less than 1, and if it comes out otherwise, that probably indicates that an error might have happened somewhere. So what is the probability that the sample mean So that tells us that this is a sampling distribution problem, and because that's the case, we also know that we're going to need to have a specific sample size. So a sample of 50 leads us to lowercase n, sample size is 50. And the specification is that the sample mean of that sample of size 50 falls within $1,000 of the population mean. So first thing, let's go ahead and see if we can come up with the correct endpoints that we want to use for this distribution. So let me first of all jot this down as 27,100, the population mean, plus or minus 1,000. And go ahead and do the math on that. That's going to give us a lower boundary of 26,100 and an upper boundary of 28,100. Okay, we're off to a good start here. So let's go ahead and sketch out our distribution. So because our sample size is 30 or higher, even not knowing the characteristics of the population distribution, we can assume normality for the sampling distribution, and therefore can use our z tools with it. So I'm going to go ahead and label this axis x bar. This is one big difference that helps you to identify a chapter 6 problem, which looks at one individual value from a population, in contrast to a chapter 7 problem that always looks at one individual sample mean of a given size. So I've labeled this axis x bar, and I'll go ahead and jot my mean on there. Let's go ahead and, while we're thinking of it, compute the mean of the sampling distribution of the sample mean. That's equal to mu, which is equal to 27,100, and we're going to need the standard error coming up, so let's go ahead and compute that. Sigma of x bar, the standard error or the standard deviation of the sampling distribution of the sample mean, you could also think of it as, is equal to the population standard deviation divided by the square root of sample size. So in this case we have one population standard deviation, 5,200, and we're going to divide that by the square root of n. N in this case is 50, and that's going to wind up at 735.39. So that is our standard error for this problem. Okay, back down to our distribution. Let me go ahead and draw our upper and lower boundary values on here. And referring back up to the question, what is the probability that a randomly selected sample mean of size 50 would fall within $1,000 of the population mean? So therefore, the area that we're interested in describing, I'll go ahead and shade, and the answer to this question is going to be the probability or the percentage of the whole 100% that falls within this shaded area. And in order to solve that, what we're going to go ahead and do is convert our two x bar values over to z values. So the lower x bar value, which is 26,100, we'll convert over to z by taking the x bar value, subtracting from it the mean value, and dividing that by the standard error value, 735.39. So we'll finish this math out. Negative 1,000 divided by 735.39, and that's going to give us a lower boundary z value of negative 1.36. All right, let's go ahead and do that again, and we'll compute that upper z value for our problem. So x bar upper is equal to 28,100. So we'll do the same process here and divide that by 735.39. So doing the math on that, we have 1,000 divided by 735.39, which is going to come out to positive 1.36. 1.36. All right, great. And now that we have both of our boundary z values, we can go ahead and figure out what the exact probability is that we're interested in. So I'm going to go ahead and write this out as the probability that z will fall somewhere between negative 1.36 and positive 1.36. So next thing I'm going to do is I'm going to go to my z table, and first value that we'll look up is that negative 1.36. So let's go ahead and figure out exactly how much area negative 1.36 has to its left. Negative 1.3 is right here, and 0.06 added to that, add those two together, gives us negative 1.36. So the area there is 0.0869, or about 8.7%. And likewise, we can flip the chart over, go to positive 1.36, and that's going to give us an area to the left of that value of 91.31%. So I'll go ahead and draw this on here. 91.31%, getting a little crowded in here. So now that we know these two crucial areas, what we'll do to finish this problem up is take the larger of the two areas, 0.9131, and from that area, which includes all the area that we want plus this left tail area that we don't want, we're going to remove the area of the left tail that we don't want. So minus 0.0869, and do the math on that. So our answer for part A then is that the probability of a randomly selected sample mean new vehicle price for a sample of size 50 being within $1,000 of the population mean is 82.62%. All right, let's move on to part B then. Almost the same setup here. The one difference being that instead of a sample of size 50 as in part A, we're now working with a sample of size 100. So let's go ahead and sketch this distribution out. So 100 being greater than 30 allows us to use the normal characteristics, and $1,000 above and below the population mean will be the same as part A. So I'll go ahead and sketch those on my curve. And this is going to be an X bar distribution or sample mean distribution. And go ahead and record that mean value there. So let's make our boundaries, shade in the area of interest. So thus far in part B looks identical to the start of part A. Now what's going to change up here? the mean of the sampling distribution is equal to the population mean. That has stayed the same, so that's 27,100 still. But the standard error value, which is equal to the population standard deviation divided by square root of sample size, is going to change. Because our sample size changed, we're now going to divide that by the square root of 100, or 5,200 divided by 10, which is equal to 520. So with a sample size of 50, notice that we had a standard error of roughly 735. Now by increasing that sample size, we've reduced the size of that standard error. So let's see what happens on this distribution. The first thing we're going to do is compute our lower boundary z value. So the z for our lower boundary, 26,100, is equal to that lower boundary sample mean value minus the population mean divided by our standard error. So here we're looking at negative 1,000 divided by 520, which works out to negative 1.92. And let's now go ahead and find the area that corresponds to the left of negative 1.92. So the probability of z being less than negative 1.92 is negative 1.92 0.0274. 0.0274. So we've now defined the area here, but let's keep in mind that because this distribution of sample means is known to be normal, we can use the rule of symmetry to save us some work here. So because this graph is symmetric, let's pretend that my drawing's to scale and that it is symmetric. That tells us that the area in the right tail must equal the area in the left tail and also be 2.74%. So therefore, to put a number on the centered area here, we're going to start with 1, or the whole 100%, and from that we're going to subtract 2 of these tail areas. So left tail, right tail means we have to subtract it twice, and that's going to give us 1 minus 5.48%, which is going to work out to 94.52% as the answer to this question. Good job on that one. Let's move on to part C. And here we have, within what range should the middle 95% of the sample means fall? So let's think about what they're asking us here. Parts A and B both ask us to compute a probability that corresponded to an upper and lower x-bar sample mean score. So here we're asked within what range should this percentage of the sample means fall. So that tells us that the answer to this question is going to be a lower and upper sample mean value. So let's go ahead and start to sketch this out and slide this up. So we're talking about a middle 95%. So here's our normal distribution, and we're now going to label this Z because we're going to be working this one using the backward technique. We're going to start with our area, and because we know this is the middle 95%, I can make symmetric marks here, and that's going to represent 95% of our area. So the middle area, by the definition of this problem, is 95%. And we're interested in what specific sample mean values will correspond to the upper and lower boundaries that we've drawn here. So first thing we're going to do is find the z numbers that correspond to these boundaries. So logically, this is symmetric. 95% of the area is contained in the middle. So how much area must be in each tail? And the answer to that is 2.5%. And so I'm now going to use my z table and go to the z table, because 2.5% is less than 50%, and I want to look up the area to the left of the z value. I'm going to go to the negative side of the z chart, and I'm going to look around in the middle here until I find the closest value to 0.0250, and it looks like here we have an exact match for that. So that is going to give us a z value of negative 1.96. Negative 1.96 is our z value there. And by the symmetry here, we can go ahead and label this one as positive 1.96. And let me go ahead and calculate the lower boundary value of the sample mean that corresponds to z negative 1.96. In this case, we're going to use the backwards equation, which says that a sample mean is equal to the overall mean added to z number of standard errors. So we'll populate this equation, 27,100 plus z, in this case my z-score is negative 1.96, and I multiply that by standard error, my sample size being 100, as in part B, tells me that my standard error is going to be 520 here. And we'll go ahead and solve this. 27,100 minus 1019.2 is equal to 26,080.80, and because I know that the lower boundary is exactly 1,119 units below the mean, to come up with that upper boundary, what I can do is start again with my mean. In this case, just flip around that minus, and instead of subtracting that amount, we'll add it. That's going to correspond to 28,119.20, thus giving us a final answer for part C of $26,080.80 to $28,119.20. Thanks for watching.